Hey guys, welcome back to Dynamics video series. In this video, we're going to get back to our special points discussion. This video is going to focus on a temporary contact condition with special points. So in this problem, as you can see, or as we'll get to, we're going to have two bodies that are going to be interacting, the red gear and the blue vertical rack. Now, they're only going to be in contact for a brief moment in time, right? They're not going to be in permanent contact. So this is a temporary contact problem, and we'll look about how that affects the velocities or how you should think about this. Okay. So moving forward, the question reads that the red gear is fixed in its center and rotates. The blue vertical rack is also a gear, right? So it's got gear teeth. So both of them have gear teeth. That lets us know there's going to be a no slip condition. So neither of these are going to be slipping off each other. And is pulled up with 2 meters per second, right? So that's the speed it's moving vertically. The radius is 0.7 of the blue gear. The blue fork rotates about its bottom, and the black dot is fixed to the red gear. Rotates about its bottom. The black dot is fixed to the red gear and is trapped between the fork on the sides, right? So that's just saying that little black dot in the fork and on the red gear is going to be stuck to the red gear and moving in and out of that fork. The distance L is 0.9. So let's write that down. So this is 0.9. Make this marker a little bigger. And the angle right now, theta, is 30 degrees. So this is a 30. Okay. And then we have two what's called questions here. What is the angular velocity of the blue fork, right? And then what is the time rate of change of L? Okay, so let's do that. So we want to know angular velocity of the blue fork. I'm just going to label that variable as WB. So that's what we're looking for. Okay. And then rate of change of L, right? So when we're looking at this L distance, the time rate of change, it's just going to be the dot term of the L, right? So just L dot. So that's what we're looking for. All right, so let's write down stuff that we know. So we know that this blue gear is being pulled up at 2 meters per second, right? So 2 meters per second. Right? So that's how the whole body is moving. We also know, and that's about it actually, that this radius is 0.7, right? And yeah, that's it. So there's some things we can extrapolate, right? Let's create our special points, right? So what's the criteria for a special point? A special point is anything, it's got 3 criteria basically. Anything that we know what it's doing, right? So things like fixed points, we know what they're doing. Things that are given to us, like this blue rack, we know what it's doing. Things that we want to know what they're doing, right? So if we're asking for like the velocity of a point, that's a point that we're going to want to label as a special point because we want to know what it's doing. And then finally, a point that's touching 2 or more bodies, right? So a point touching 2 or more bodies, it relates the velocities in some way or the acceleration in some way. That is also a special point, and that's something we have to look out for. So I see 4 here, right? So I'm going to see this one right here. This fixed point, we know what that's doing. It's doing nothing. This point right here, it's a little weird since it's already black, but I'll label it in green, right? And then this point down here, right? We know what that one's doing. I'm going to label these just kind of arbitrarily. So let's say this one is, I don't know, point A, point B, point C, and point D. Okay, so these are my 4 special points I'm going to use. The first thing I'm going to do is I'm going to look for a shortcut, right? So what are the criteria for a shortcut? So for a shortcut, we want to know one of 3 things, right? We want to know a distance between them, which is usually that's given. But the main things we want to know is a velocity of a point or an angular acceleration of a body, right? We need to know 2 of those things to solve for the third one, right? In this case, we can use the shortcut when we have a fixed point connected to another point that is not a relative term, right? So if we have like this case where we have B, right, is a fixed point, and then it's a fixed distance from A, 0.7, right? And we know the speed of A, we can solve for the angular velocity of this red circle. Now, why do we know the speed of A, right? I said it, but why, right? So it's 2 meters per second. I get that from that the rack is moving vertically at 2 meters per second. If you guys look at your chart, it's on the front of the cover page, or it should be in your OneNote. You'll see that for 2 things that are in temporary contact with no slip, if you go to the velocity column, they're going to have identical velocities in plane, and they're going to have the same velocity in the normal direction, right? So for these 2 things, where this gear, right, this gear here with these teeth, and then this rack here with these teeth, they're in temporary contact and they're not slipping because of the gear teeth, we know that at that point, or at any point A, that point A is going to have the same velocity as this blue rack, right? Since the blue rack is moving upwards at 2, we know A is also moving upwards at 2 at this moment in time. right? So since we know that velocity of A, we can do two things. We can write that we know the velocity of A equals just, this is the shortcut now, the distance between A and B, and the angular velocity of this red skier, right? Because that's the body that they share, right? So since we know this, we know the velocity of A is 2. We know that the distance between A and B is 0.7, right? So we know that the angular velocity just has to equal, okay, angular velocity of that gear equals 2 divided by 0.7, or about 2.86, right? And that's in radians per second. Right? Now, I didn't give you a direction. Now, you can write this initially as vectors and figure out the direction that way, or you can just look at it and kind of intuit it. So we know that A is going up, right? So it's going in this direction. So this gear is probably rotating like this, right? Or it's definitely rotating in the counterclockwise, right? Since it's going counterclockwise, we'll write that out. And that means that counterclockwise is our positive k vector direction, so this is going to be in the positive k, right? So whenever we write that in our velocity equations, we'll make sure it's in the positive k. Okay, so that's the first part. Moving on. So that was the easy part of the shortcut. Now we have to analyze the relationship between B and C, and then between C and D, right? Since we want to find out the relative velocity term in this slot, right? And also the angular velocity of that blue fork. So we're kind of just looking for everything about the blue fork. All right, so next we're going to do the velocities between C and B. Now I'm going to do one thing. I'm going to put the velocity of C on the left side for my CB equation. And I'm going to do the same thing. I'm going to put the velocity on the left side for my CD equation. So this is my CD one. I'll put it preemptively. This will be my CB equation. I'll also put it preemptively. Right? I'm going to put VC on the left side for both of these equations. Why am I doing that? I'm doing that because VC is the shared point between this CD and CB, right? They both share C. And so it's going to be easy if I create these two equations with VC on the left side, because then after I'm done making the equations, I can just algebraically equal them to each other, because they'll both be equal to VC, right? So I'm going to write whatever on the right side of these equations. And when I make them equal to each other, I can just solve for I and j components straight away, instead of finagling with some algebra trying to get the same term on both sides of both equations, right? So this would be easier. You can do it the other way. It would take a little bit more time. On exam, you might not have enough time. But this is how I would do it. All right, so let's analyze C and B. Okay, so we know that the velocity of C, and then I'm going to use the equation on the cover page, equals the velocity of B plus the angular velocity of whatever they share. In this case, it's the red gear. Cross product of the position vector from what's on the right to what's on the left, right? So it's going to be from B to C. B to C. Okay, and then plus any relative velocity terms they may have with each other. That's going to end up being 0 because they're a fixed distance apart. So let's continue. So VC equals, and then VB. VB is a fixed point. That's what we know about it. That's why we labeled it as special. So that's going to have a 0 velocity. And then plus the WR, right? And we said already that the WR is what we solved for. That was positive 2.86 in the positive k direction, right? And with the cross product of the vector, the position vector from B to C. Now, you can see that's going to have two components, right? So it's going to have a vertical and a horizontal component. So it's going to have an I and a j component. I'll write it out just to be explicit about it, but we have an I going positive to the right, and then a j going positive upwards. Keeping this sign convention keeps our counterclockwise as the positive k, right? If you switch it up and you want I and the negative going left as positive, then it might switch to the k value. So just keep that in mind. I would just stick with the one I already, stick one with the one I already have drawn, just because it keeps k counterclockwise as positive, right? And you can always just remember that. But the world is your oyster. So we have this angle that's 30, right? And so since this angle is 30, we know that this vertical distance is the sine of 30, right? So I'm going to put that there. That's the sine. And then this part is the cosine, right? And then that distance they are from each other, or that magnitude, is 0.7, right? So in the I component, since we're going left, it's going to be a negative I. So this is going to be negative 0.7, that distance, times the, and we said I was the cosine, so cosine of 30. Yes, and then we have plus, because we're going, oh no, it's still minus because we're going down. So this is still minus, and then now we're going down into j, so this is now the sine of 30, right? Don't be foolish like me and forget to put your i's and j's. So remember, this was I and this was j. Cool. Perfect. And we have no relative velocity term. C and B are always going to be that 0.7 meters apart. Absolutely. So no velocity term there. Relative velocity. Okay, so now we can do this cross product. So VC equals, and then remember how we do cross products is we multiply these constants, right? So I'm going to multiply 2.86 times the negative 0.7 cosine 30. So let's do that. So 2.86 times negative 0.7. I'm doing it on my calculator right now. Cosine of 30. And that is negative 1.73. Okay, so that's our constant value. And then we're doing a k times I, which gives us positive j. So I'm going to put j. I'm going to leave the sign the same. Cool. I'll erase these underlines. Okay, next. And now I'm going to do, again, this constant term times this constant term, right? So I have 2.86 again times, but now it's 0.7 sine of 30, so 2.86 times negative 0.7. Now it's sine 30. And that gives me negative 1. So I have negative 1. And then when I do this, I get k cross j, which is negative I. So I put an I and I flip this sign, right? And now we have our I and our j components from that equation. Okay, now we can do our CD equation, or the equation for this blue fork. So I'm going to analyze C, I'm going to analyze D. So VD, right? Plus, and then relative velocity of the body they share. In this case, it's going to be the fork. I put it as VB in my thing down below. I probably just did that because it's blue, but you can put VF for fork if you want. And then with the, assume it's in the positive K. Let's make that assumption. With the cross product from, what is this? From D to C. And then plus any relative velocity terms. So I know that there will be a relative velocity term here actually, so we can write that in a sec. Because there is a slot that this point is sliding through. So VC equals VD. Now VD is just going to be 0, right? Because VD is a fixed point, or D is a fixed point. And then we'll keep WB, right, in the positive K direction. And then with the cross product, and then the distance from D to C is a vertical distance, so it's only in the J. And we're going up the distance L, so we're going up 0.9 meters. So this is a positive 0.9 in the J. Cool. And then plus this relative velocity term. If you can notice, the relative velocity or the distance that changes between C and D is just the same as the change in L, right? So that's just going to be our L dot term with respect to time. And then at this point, L is completely vertical, so that's also going to be in the J component. Cool. All right, so let's do this cross product. So VC now equals, that's a weird C, VC equals 0.9 times WB. I'm just multiplying the constants, so 0.9 WB. And then now it is K cross J, which is I with a negative I. And then we have just this other term plus L dot in dj. Cool. All right, so now we have our two equations. So we have this one up here and we have this one down here. And they both equal VC, so we can actually just equate them to each other. So in my I component for this equation, let me just block this off a little bit. In my I component for this equation, right? Since I and j are orthogonal to each other, we can just equate the I components of that first equation to the I components of the second equation. When we do that for the i's, we get that 1 equals, and then the i's from the right side are negative 0.9 WB. And then in the j side, we get that from the top equation, negative 1.73 equals, and then from the bottom equation, L dot. Right? So when we solve for both of these, right, two equations, two variables, we'll get that WB is equivalent to negative 1.11. What does that negative tell us? It tells us that this thing is not in the direction that we wanted, right? So we said it was in the positive K. Since it's a negative value, it's actually in the negative K. So this WB value is actually going clockwise, right? Because clockwise relates to our negative K. So that's the answer there. Okay. And then, and this is radians per second. It's a little smushed, but radians per second. And then L dot, this is the easiest one to solve. It's already solved. So we would just put that L dot equals, right? So the rate of change of L, right? So L is getting smaller. So point C and point D are getting closer. Would you imagine how the thing spins? Makes sense. Is negative 1.73 meters per second. All right. So these two points C and point D are getting closer to each other. And yeah, that's going to be about the end of this problem. So I guess the biggest thing here is making sure that you can relate the velocity of this blue rack to the velocity of A, or this point I made up in this case, and that you know how to write out these equations, making sure to keep out the sign convention the same. So if you multiply a k times an I, make sure it's a positive j, and then a k times a j, make sure it's a negative I, stuff like that. Don't forget to do your cross products, and if you have a VREL, make sure to include it, because that will completely mess up a problem. That's going to be the end of this problem. See you.